Amazing, awesome. Hello, everybody. I'm Khalid AlNujaidi. I am a student from Prince Mohammad bin Fahd University. I have Ghadah AlHabib. She is also a co-author that worked on this research project with me as well. Our research project is under the title of Computer Vision for a Camel-Vehicle Mitigation System. The motivation for this research is that wildlife and vehicle collisions is a problem that happens all over the world. Usually in different continents, it's like different animals that are the cause of these accidents, the car accidents and the collisions with the vehicles. They are both very costly in terms of property damage and as well as they can lead to fatality and physical injury for the individuals that are occupying the vehicles. Camels especially are more fatal than other animals, just for the fact that their physical build is somewhat different than, say, deer or moose, which are some of the common animals that are cause of vehicle and wildlife collisions. The camel is like an animal which like the majority of its mass lies like very high from the ground, and he has like long legs, which usually result in like it falling over the windshield and causing a lot of damage for the occupants. Within Saudi Arabia alone, there has been recorded over 22,000 accidents related to the camel. This is based on the data that has been received from the Ministry of Interior. These statistics are recorded over the span of 3 years. Unfortunately, even though these accidents usually result to like deadly outcomes, the exact numbers of like the severity of the injuries of these accidents is not publicly available or well recorded, though like a simple internet research of looking up camel accident, car crash would result in unfortunate results that show the severity of such a problem. The focus of this work and the project is to look into the possibility of approaching a camel vehicle collision avoiding system using state-of-the-art artificial intelligence models. Specifically, we will be using object detection models, which fall under the computer vision category of computation. This is to then further trying to develop a fully automated system that would rely completely on computers identifying the camels crossing the road, or it could be other animals as well, can be easily integrated into all environments, just based on the ability of the computer to recognize what is inside the image or video, or just in general what the camera sees. There have been like works that have tried to tackle this issue of camels causing vehicle accidents in Saudi Arabia and neighboring countries, but these like solutions have not been like very practical, as we could say, because they are not very autonomous in their nature. They require the collaboration of the farmers, the camel owners, the people who like own the animals, as well as they don't take into consideration the camels that roam freely, that are not owned by anybody. These solutions range from the integration of geolocation tracking of the animals, creating applications, phone applications to see the locations of them, putting trackers and like chips on the camels, and putting like sensors of nodes across the roads, so that when the camels become close to the roads, these alarms are sent off to the authorities and the owners of these camels, as well as implementation of night vision cameras on vehicles for like the occupants to be alerted if there were like an animal to come out in this situation, a camel. But all these solutions have been proposed not only for camels, but for animals and wildlife in general across the world. And no such system has been proposed using a fully autonomous computer vision-based system. So computer vision, briefly, starting from the beginning, how it works in a abstract way. Here we can see a image of a camel. Us as people, we can just look at the image and we see that it has the shape and it appears like a camel. We just know it. Though for computers, how they see images is basically just pixels, like zeros and ones. And an image can be viewed as a two-dimensional matrix, as in it has rows and columns. And as in this example, there are like 5 by 5 columns and rows, each of which represents a pixel. And the pixels their values can range from 0 to 1, or from 0 to 255, depending on the amount of color is within the image. Though the world is not in black and white, the world is colored, and everything now is in color format. So the images are usually in RGB colors, and this adds a additional dimension to the 2D matrices, as in their images become a tensor of 2 by 2 by 3. For every 2 by 2 dimension of the pixels, there's a dimension for the red or green or blue colors. The tasks of using machine learning and AI for computers to identify and understand what's in the picture can be classified between either classification or localization. Before, like at the start of using these advanced deep learning methods of understanding what's within images, at first they just did not consider where the item was within the image. They just took the entirety of the context of the image. But when computers and algorithms advanced and newer methods of approaching this issue of understanding what's inside of the image, there has been algorithms developed to even localize the object of interest in an image. As we can see from these two pictures, on the left, we can see that there's a camel in the picture, but on the right, we see exactly where the camel is. The data set that we used for these experimentations consisted of about 250 images of the camels in different contexts and environments. Uh, there's some pictures as well here, as we can see. Some images are of them on the road. Some of them are in the desert. These images were collected from either like YouTube videos, screenshots of YouTube videos, or like through the process of using some Google Chrome extensions that enable to download mass numbers of images by just searching a word, which was the process used for building this data set. Though part of the contribution of this work and research is to provide and share a data set that we believe, and we did not find any similar data set that exists, of 250 labeled images of camels. As the picture represents here, each pixel is also provided with a formatted either text file or Pascal file or XML file or CSV file as well, different formats of where the camel is located within the image. This is important because the algorithms we are using for this computer vision tasks is not only image classification, but we are using object localization as well. It is important to understand where the camel is within the image, because if it were in the middle of the desert for our system, this is considered safe. But when we understand the context of where it is, and we can segment the road from the camel, and we can see that they are close by, this provides us much more context and helps us more in trying to reach a conclusion or do a particular task. So like with these images and labels, it is even more efficient for the computer algorithms to learn, because there is a lot going on in the image. But when we provide the algorithms with these images and the labels, it can ignore everything else in the image and just go to where the drawn squares are. So it can extract the details and features and just the things that represent the camel. How these images are understood by the computer is mostly now either through convolutional neural networks or vision transformers. These are deep learning approaches for image classification and object localization tasks. These methods used in this research are the convolutional neural networks. The CNNs, also known as CNNs, these CNNs are inspired by the mammalian visual cortex, just like how animals and people see. It's usually when they first look at something, they have different processes of like interpreting the thing. At first, the person sees the shape of the object, then they see the depth of the object and how far it is, and then the color, and just through extracting these different things and putting them together, they reach to a conclusion and understanding what this particular object is. And this is what the algorithms, the CNN algorithms, tries to represent through the process of convolutions and poolings. Given an image, the algorithm first takes a kernel or a filter that goes over the image until it covers the entirety of the image. These kernels are also a 2x2 or 3x3 matrix or tensor that produces the dot product while scaling and going over the original input image. The product and what it produces, this convolution layer, is usually a desired trait that we want to extract from the image. It could be either the color or the shape or the edges, whether it has a lot of vertical or horizontal edges, it has fur, or it has like a wooden texture, just these different types of features. While the following pooling layer just compresses everything and reduces the dimensionality of this convolution layer. This is very important because images now are not like the previously seen image of like 5x5 picture or like columns and rows. Now the pictures on our phone take like a 3000 by 4000 dimensional image. There are many pixels in the image, and that would result to a lot of computations. So these convolutional and pooling layers help extract what's important in the image to then feed into a neural network, a fully neural network, which then that's where the process of learning and identification is after extracting the features. For object detection, it is also based off of the convolutional neural networks. There are different algorithms and implementations of the convolutional neural networks for the object detection tasks. Usually it's like in an abstract manner follows the convolutional and pooling layers, though at the end when it reaches the neural network then produces or is faced with two problems that it outputs and needs to solve. It then becomes a probabilistic problem of trying to figure out what is inside the image, the class of the image, as well as producing a regression problem for finding the most optimal bounding box or square that highlights where this object is within the image. For these experiments, we experimented with 4 object detection models: the CenterNet, the EfficientDet, the faster RCNN, and the single shot detector, the SSD. All these models have been archived on the TensorFlow 2 detection models repository and made open for the public. Anybody can go and download these models. That is important because these models are pre-trained. They are pre-trained on the COCO 2017 dataset, which means that these models are trained to detect different objects, and the convolution layers are used to or trained to like pick up objects and distinguish and differentiate between different objects very fast. And this then enables people or like individuals or researchers and experimenters to then transfer these learnings and make this model focus on a particular object of interest, in this case, the camel. This is known as few-shot learning as well, which is what we did through these experiments. How these models are evaluated at the end is usually through a few matrices. Most importantly, it's the intersect over union and the mean average precision. How we get the intersect over union is through the formula that is present in the image below. It is usually the area of overlap over the area of union. And we have as well 3 examples that represent how each of these detections are valued. Typically for these models, they are evaluated on a restriction of 0.5 to 0.95 to be considered a true positive detection, because the detection can as well cover a large majority of the image, and over recognizing the object is not good as well. This is to produce accurate results to be evaluated. Through the experimentations, we found that the CenterNet model has performed best. It has performed best over the scale of different IOU restrictions, and compared to the other models, as well as it was surprisingly the fastest model that was trained. How these models were compared was they were all trained on the same images, on the same computer, and all of them for 10,000 steps. As in, all these models for 10,000 times went over all the 250 images in a random fashion to try to extract where the images. Then they are then tested on a separate set of images that the computer have not seen. Though we as the researchers know the results of, and from that there we can then extract these values. In comparison to the other models, the CenterNet achieved the best out of them through the different IOU restrictions, as well as just in the efficiency of training. This finding shows that algorithms are truly becoming better at understanding the environment. As we've seen, the CenterNet has performed very well in compared to the other methods, and the computation of it has become more accessible and easier to compute as well. We've covered that the wildlife vehicle collisions are a global issue, and that they are having a significant socio-economic impact and resulting in a lot of damages. Camel vehicle collisions in particular are very deadly and very dangerous, and they are something that is currently relevant and can be experimented with in these areas of the world. The CenterNet, again, has been the best performing model out of all these models. The vision of this work is to then implement and deploy these findings or these models and algorithms into edge devices that can autonomously work and set off warnings and just to scare off the animals off the roads by themselves fully autonomously without needing the intervention of the camel owners or the authorities to come to the locations. This has been our work and our findings and our vision for the future. Thank you very much for listening. If anybody has any questions.